Thank you. Hello, hello.
Hello. I did not have the fanfare queued up for you this
come
week.
on.
I'm terribly sorry about that.
How are you doing, Chris?
I'm doing all right. I thoroughly enjoyed the discussion last week of who is the physicist, Sir Isaac Newton or Albert Einstein. I thoroughly enjoyed that conversation. And as we decided afterwards, the neutron stars would be the topic this week.
Neutron stars. Yeah. Those are fun.
Well, from what I understand, and correct me where I go wrong, they are stars that start to collapse and become this very, very, very hyperdense thing. Are they failed black holes?
Well, so I would say that perhaps black holes are failed neutron stars. I would flip it around. So what happens really is you have a star, perhaps a little bit more massive than the sun. And the reason the sun doesn't collapse, the sun has a lot of mass. So you would think, there's gravity and gravity is strong. So it should, pull the mass in the sun into a single point. But that doesn't happen. The sun has been there for a while. And that doesn't happen because there's pressure produced by the burning of fuel. So the sun burns hydrogen, and that produces photons, and that produces something we call radiation pressure, which effectively counteracts gravity. So this pressure is fighting gravity and preventing the thing from collapsing. But, as we all know, fuel comes in limited amounts, and even the sun can run out of it. And so when the sun runs out of hydrogen, it needs to do something else. It will, in some sense, contract, heat up, the temperature will increase, and it will start burning something else that the sun has produced as a byproduct of burning hydrogen. And what that is helium. So it'll start burning helium, which is the second element in the periodic table, until it runs out of helium. And then it'll move to the next element, and so on, until it eventually hits iron, because it's not energetically favorable anymore to burn iron. So what happens is the stars have this iron core after they've burned through all of this other material. And at some point, there's nothing else to burn, so there's no more pressure that can be generated to fight against gravity. So then the whole thing collapses until electrons inside of the star get packed so close together that Pauly yells out, "No, you can't do that. I told you that objects that had identical features that also had half integers, they could not occupy the same state, blah, 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 quantum mechanics, my head explodes." But what really is Pauly is telling you is that you can't really put two electrons too close to each other. Mm-hmm. And a pressure emerges, a quantum pressure. And we call that a degeneracy pressure, and it prevents the star from collapsing further. And when you have a star that's stable under electron degeneracy pressure, so this degeneracy pressure is fighting against gravity, we call that a white dwarf. Okay.
Gotcha. Okay.
But, sometimes there's still additional material outside of this iron core, and it's still, this additional material, these outer layers of the star might still be burning something and might still be dumping more iron into the core. So you might be adding more material to your white dwarf, until eventually there's so much new material that gravity is stronger than electron degeneracy pressure, and it wins again. So now the whole thing collapses more and more and more and more. And so now what happens? Well, electrons begin to interact with protons. And through something called electron capture, electron plus proton leads to neutron. Mm-hmm. Okay, so, like an atom, like hydrogen atom, it's a proton, and it has you think of it as really an electron going around the proton, mm-hmm. and you know that the proton has a positive charge and the electron has a negative charge, and if I put two of those together, I can effectively form a neutron that has no charge, at least if you put enough pressure to allow for electron capture. So when this happens, you form all these neutrons, mm-hmm. and the neutrons. So you're contracting the thing, and you have these electrons, so you have these protons, and they're forming these neutrons. And the more you contract it, the contract the star, the more neutrons you get, until eventually you have this ball of neutrons. But then again, Pauly comes in and says, "No, you cannot put two neutrons too close to each other because nature abhors small spaces," or something. Mm-hmm. So now you have this new type of degeneracy pressure that we call neutron degeneracy pressure, but it's the same idea. You can't put two neutrons too close to each other. They don't like each other that much. So then what happens is gravity is prevented from collapsing the star because of this neutron degeneracy pressure. And if you have a stable star like that, we call that a neutron star. But it is still possible that there's more matter that's about to fall into this neutron star. Okay? And if that happens, if the star you started with was massive enough, okay, such that by the time you form the neutron star, there's still mass out there that can continue to fall or accrete onto the nucleus, then gravity can beat neutron degeneracy pressure, and the whole thing will collapse further. And at that point, there's no beating gravity, because gravity always wins. And at that point, after the star has collapsed enough, much further from the radius of a neutron star, then you form a black hole. So the black hole is the ultimate state. And if you want, you start with your initial state being a regular star, and then you transition perhaps into a white dwarf, and then you perhaps transition into a neutron star, or perhaps you just go directly from the regular star to a neutron star. And eventually, if there's enough mass, you end always with a black hole. If there's enough mass. If there's not enough mass, you can end up with a neutron star, and that's perfectly fine. Of course, in the process, there's this also small little additional detail of there being a giant explosion that we call a supernova, because, as you're producing this gigantic amount of contraction and pressure, then something called neutrino is produced, and the outer layers of the star get exploded, or like they fly out violently and form a supernova explosion. So that's, by the way, the history of the life of a star in like 5 minutes. Well, thank you.
I appreciate it. It's not that easy to do, but I think I understand that. The history. So the sun is currently in a state of equilibrium. Yeah. Although it is slowly deteriorating. Yes. It is my understanding that the history of our sun is, as it deteriorates in the final billion years, it will expand, the size of the sun will expand to encompass the orbit of the Earth, and then it will collapse. Yeah. So that is true.
Yeah, it'll take a very long time. It will not form a black hole because the mass of the sun is not that large, at least not based on what we understand. It'll just form a white dwarf and just like hang in there.
So going back to the black holes where gravitational waves were detected coming from. Yeah. They had to be massive stars to begin with.
Yeah. Yeah, we don't know how to make those. Yeah, so we thought a neutron star, okay, so that people understand, is a star that has roughly the mass of our sun in a ball roughly the size of Bozeman. Okay, so you get an idea. It's a ball with a radius, about 10 kilometers. Okay. Now, the objects that the black holes we've detected, the small black holes that we think exist out there, at least we have scenarios where these black holes could form. These black holes have maybe 5, maybe 10, maybe 15 times the mass of our sun. We don't know how to form a black hole that's 30, 35, 40 times the mass of our sun. It's not easy. We don't have data that suggests that these things form except for this gravitational wave observation. So there's lots of ideas and hypotheses out there. What if you had a star that was very, very massive and as it's collapsing, then it's spinning very fast, and then it separates into two black holes. And now you have two black holes that are very massive, and they're orbiting around, and eventually they merge, which is what LIGO saw. That's one hypothesis, perhaps somewhat unlikely. But,
It's 1450 KMMS, 1340 KPRK. MSU Professor Nico Yunes in the studio. Why are neutron stars important in our understanding of the universe?
Of the universe. Okay, well, that's a different question.
Oh, sorry. What did you think I was going to ask?
I thought you were going to just say, why are neutron stars important, period, go.
No, but why are they important in our understanding of the universe? Because I think understanding of black holes add to our understanding of the universe.
Yeah, absolutely. So neutron stars, there's a lot of them. So we think there's about 2,000 of them in the Milky Way. They're very exotic, and the gravity on the surface of neutron stars is immense. I was reading that, if you, I don't know who calculated it. I actually did not check this calculation, so it may be wrong, but hopefully not. If I take, a chair that weighs 1 kilo on Earth, and I just drop it from 1 meter from the surface of a neutron star, by the time it hits the surface of the neutron star, it will have completely disintegrated due to the collision. That's how much gravity, how much force there is. And it will be traveling at, 2,000 kilometers per second or something like that at an absurd velocity in just a tiny amount of distance. And these things are so massive that a tiny teaspoon of, neutron star material would weigh like 900 or 1,000 times the Pyramid of Giza on Earth. Ooh. Okay? You're talking about, a matchbox of neutron star matter weighing like 1 trillion tons or something like that. It's just absurd how much mass there is. And so because of that, they're very, very interesting. And they have very, very crazily strong magnetic fields. And because they have very strong magnetic fields sort of, they are sort of the highways of photons, okay? That's photons like to travel along magnetic field lines. And so the magnetic fields of neutron stars sort of look like funnels. And so the photons that get produced, the light that gets produced by a neutron star gets funneled in these like beams that come from one pole and from the other pole. And because the magnetic field, this funnel structure of the magnetic field does not coincide with the spin axis of the object, effectively as the neutron star is spinning, the beams of light are moving around like lighthouses. Okay, and every time we're standing on the shore or on a ship, every time the lighthouse beam crosses you, it's like, there's a lighthouse over there. So they're like the lighthouses of the universe. We can get really, really interesting information by detecting the radio pulses that they generate. That's why we build enormous radio telescopes. Arecibo, for example, where Contact, I think that was Contact. I think the Contact was filmed, that movie with Judy Foster.
Yes.
Yeah, we're old. Yeah. I actually brought that up to my students, and they're like, what Contact? What's that movie? Who's Judy Foster? Jodie Foster. Yeah, anyway.
So that leads me to my next question. Neutron stars, even if I bought a really good telescope at the hobby shop, I could not see a neutron star in the night sky. Would you like me to take a break, sir?
No, I'm good. Okay. I'm good. I'm just a little bit under the weather today. But that's correct, because the amount of they do emit light in the visible spectrum, but it's so weak you would never be able to see it. You would have to see in radio waves, in a different spectrum of light. And we don't, regular telescopes, our eyes are not good detectors. They're really, really, really bad detectors. Even animals have better detectors than we do. Right. So you have to build a better piece of equipment. You have to build a giant dish controlled by a computer. You know that was like our idea. I mean, not mine. Right. This was like in the 50s. But physicists and astronomers were like, if we build a giant dish and we control it with a computer, well, it was like more in the 70s, then we can detect really, really weak signals. And, nowadays, all dishes in telecommunications are controlled by computers. Right. That's when you talk about satellite TV, that's what is being used. Like, not the satellites on your house, of course, but the satellites in the main stations are broadcasting. That's like perhaps the most obvious spin-off of radio astronomy.
The one thing I'm starting to notice from our conversations is if physics is only as good as the instrument being used to measure whatever, or to be able to detect whatever. Because then you say, I think this may be out there, but we have to build this machine to detect it. And then once you have it built to detect it, you need to have to build the machine to measure it again.
Yeah. So, I'm a theorist, right? So I'm not a physicist in theory. I'm a physicist that works in theoretical physics. So I am the first to recognize that experiment is what drives, and observation is what drives progress in some sense. But you also have to have a good idea. You also have to come up with scenarios and models and predictions and things you can go and look for. Because if you're not given any guidance, then you don't know what to look for and what to build. You're building very specific machines to do very specific things. And if you don't know what you're going for, it's impossible to find anything. Yes, you can just build a new instrument and shoot up in the atmosphere, turn it on. It's like, let's see what happens. Let's see if the Russians are experimenting with nuclear weapons. Oops, there's a black hole over there. Yeah, that actually happened, people.
Really?
With X-rays or gamma rays, I forget. Yeah. So this was like in the 50s. Don't exactly recall this story, but the idea is that the U.S. and Russia, there was Cold War, and you were sort of monitoring each other's, like who's doing nuclear testing and nuclear experiments. So they put a bunch of satellites with X-ray detectors. I think it was X-rays. Yeah, X-ray detectors in orbit, pointing at Earth, and they kept on getting this noise. This like blips of noise that kept on going on. Like, what's going on? And they realized that these blips weren't coming from Earth. They were coming from the other side. They were coming from the universe. And that eventually opened up the field of X-ray or gamma ray astronomy. I keep on forgetting which of those two, this story reflects on.
You've mentioned several times in discussion of black holes, or even in the passing mention of black holes, infinite density. I don't think infinite density can exist.
Well, so let's first talk about what density is. So I've said this a few times, but it's the idea that you take matter or mass, and you say how much mass there is in a volume, in a given volume. So you take a matchbox, okay, and you stick some sand in there. So the matter that makes the sand divided by the volume of the matchbox gives you the density of that object. And when we say infinite density, we mean a really, 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 really large number that cannot be counted.
Yeah, exactly.
That's what infinity means. And there's different types of infinity.
Oh,
it turns out there's like a regular infinity, like the infinity of the integers, and then there's the infinity of infinities that had to do with like fractions. So it's the mathematical topic of infinity. It's A, still open, and B, really hard to understand and abstract. People have gone crazy, it is said, by studying infinity.
Well, probably the same thing can be said about the concept of zero.
Yeah, well, zero and infinity, they're reciprocals of each other, right? So, at least one type of infinity. But, as a physicist, we take a much more pragmatic view, okay? So what we mean is, if you try to calculate what the energy is inside of a black hole, okay, then you find that the energy, as you're calculating the energy, let's say, or the mass, let's say, well, not the mass, but the energy, closer and closer and closer to the center of the object, you find that at the center of the object, there's essentially the equations give you an infinity. The equation gives you a 1/0. The equations give you an uncountable, very large number, okay? That does not mean that there's infinite energy or infinite mass at the center of a black hole at the singularity, okay? It just means that when you're approaching the center, so imagine measuring distances from the center out, okay? And as you measure smaller and smaller and smaller and smaller distances, then the energy is approaching infinity. And your equations should not really be valid for such small distances. Why? Because general relativity does not play nice with quantum mechanics. And quantum mechanics is the theory about small distances, and general relativity is the theory about large distances. So general relativity should be perfectly an excellent description of nature for large distances. But once you begin to probe the nature of the singularity, distances are 10 to the minus 30 meters or something like that, then general relativity cannot possibly give you the right answer. You need to transition to quantum mechanics, and we don't know how to do that. So the fact that you ignore that Einstein's theory is wrong in that limit and you just push it anyways and you get an infinity is just a reflection that, the theory, the equations are not valid in that limit. It's not really that the energy becomes infinite. It should become really, really large. Quantum mechanics should take over, and then the infinity should be removed. That's sort of like what we have in our heads. So it's just a manifestation of the breakdown of the theory, if you want.
And my final question to you, because we're just about out of time, Nico, would be, from all our discussions leading up to this one, gravity seems to be the principal force in physics. Is that a correct statement?
That's because I'm biased, and that's what I study, and it's all about gravity with me, and so on. But no, there's 4 forces, right? There's the strong and weak nuclear forces. That's 2. There's the electromagnetic force, which plays a role in your life, Chris, with radio. And then there's the gravitational force. So the gravitational force, if you want, is the weakest of the forces, but the one that, as we've discovered, can produce the most energy. You know, the amount of energy released when two black holes collided and LIGO detected them, was 50 times more than if you take all of the light of the stars together. You take all of the light produced by all of the stars and multiply it by 50, and still that event was more powerful. And that's all the stars in the universe, I should have said, okay? But, of course, it was not energy that was carried in light. It was energy carried in gravity. So it's not something that until now we could detect. But no, so gravity is important in astrophysics. It's perhaps one of the most important forces in astrophysics when you're talking about stars, But, even when you're talking about stars, and I'm talking about the burning of the material, then nuclear physics plays a huge role. This electron degeneracy pressure, that has to do with quantum mechanics, and that also plays a very important role. So I don't want to give you the idea that gravity is all that matters. Okay. Really, in astrophysics, unfortunately, all forces matter, and you sort of have to know about all of them and master all of them so that you can, come up with scenarios and make predictions. That's why I like to study black holes, because there's no matter, and then I can just deal with gravity.
Well, Professor Yunes, I always appreciate the time and the explanations you provide. I look forward to our conversation next week.
Yeah, absolutely. Thank you, Chris.